I will present a perspective on going quite fast through some 20,000 years. But let's see how to start with some remarks that connect to a crucial issue in knowledge construction. But this will be not the only one, but surely there is something very deep going on in the massive tool for digitalizing, discretizing the world in a very effective way. We have fantastic machines, fantastic digital machines that are changing our interactions. And their use as tools for knowledge is really a fantastic occasion for science, but at the same time, it may have a major misleading role that probably already existed when we created new tools, but never like before. There has been some sort of a marriage which is difficult to understand to some sort of social or power structure with the projection of this tool into the world. So one aspect from the point of view of an epistemology is to discuss about the discrete and continuous. Of course, the world is not discrete or continuous. It is what it is. But we organize it in very different ways with using these two tools that have some sort of rigorous mathematical meaning, but are very often used in a common sense, which may distort also their meaning. The two aspects of discrete and continuous contribute to knowledge, surely by the structure of language, as we have written it in the alphabetic frame, and the gestures, and both of them are essential for constructing meaning. I don't know if by some sort of abuse we can say that the human communicating community dared to be together when they invented, projected on the stars some shapes. You know, they were drawing contours and said, look, this is a lion, this is a bison. There is not such a thing, but the humans have been able by language and gesture to give meaning to something which is totally meaningless, to, you know, those little lights up there. We continued by drawings. You see, in the Lascaux and Altamira caves, there are various ways of representing animals. There are some that are just like spots, colored spots in brown or in black, and others, I don't know if they are before or later, they are just contours. This is an incredible step because a bison is not a contour. We, the humans, we invented those contours, and in a language, for sure, we said to the others, look, this is that animal, that horse, or whatever. So this step, which is typically human, no animal would never recognize on such a contour, a line, on a very regular rock in the background, would ever recognize another animal. Perhaps a monkey, for love of his master, can be forced to recognize it, perhaps. But surely this is typically human, and the interaction in language, I bet, in the mythical construction has been essential to this. And this goes on up to the invention of writing. I strongly advise to you the work by Clarissa Ehrenschmidt in Paris, in particular the latest volume, Les Trois Écritures. She's an archaeologist of the invention of writing, which happened in the 4th millennium in Mesopotamia. And one of these forms of writing, all of them were invented there, ideograms, logograms, alphabetic writing. One of them is really shaping our culture, the alphabetic writing, which is particularly original, I would say. In a way, is an evocation of meaning by a gestalt, by a form like in ideograms. It's just a musical notation of the continuum of language. This invention has been going together with those gestures that I mentioned before. Where is continuity? You know, as I said, it's not in the world. We do have a peculiar way to apprehend the trajectories. In order to capture a prey, or even simply to capture a ball, you have to precede it by a jerk, an eye jerk. And all the big vertebrates, as we are, do this. I mean, they have to learn. It takes time. They have to learn to remember the trace left by trajectory of an animal, of an object, and then precede it in order to capture it. And this is a gluing of retention and protension My personal cognitive interpretation, on which I've been writing some 10, 15 years ago, is that this gluing is the origin of the judgment we make of the continuum, of the phenomenal continuum. If you ask to a frog whether the world is continuous or discrete, the frog takes snapshots like that. I bet the frog would say the world is discrete. The frog gets to the prey by exactly to the point where the fly is, without this complex procedure of preceding, as we do all the animals with our kind of eyes, with the fovea. So there is this continuous gestures that are the result of preceding a prey, remembering the trace, and drawings. And since Euclid is the other fantastic step after Lescaut, I would say, or Greek geometry, by a fundamental invention. Definition beta, which was written there as a definition later on, but is by Proclus or Boetius in the 3rd century after Christ. But that's not important because the definition beta is implicit everywhere in Euclid. Namely, a line is a length with no thickness. An incredible invention. Where are lines with no thickness? They don't exist. That's the invention of geometry, of Western geometry. All the Euclidean geometry is just made out of borders. The Greek invented the notion of border, which is a very difficult mathematical concept, and is absolutely needed to the practice of measuring, because if you want to measure a surface, and if the border has same thickness, which is the surface, so they invented the notion of border. And this goes together with the notion of trajectory that's been elaborated from Aristotle to Galileo as something independent from the phenomenon. Is taken away, is an invariant which allows you to do mathematics. Then this will become the continuum. The continuum of Euclid is a gesture, it's not made out of points. The definition alpha, also added later, of semeion as something that has no parts, is not really what is used in Euclid books, because semeion is a sign. Semeion is given by a letter at the extreme of a segment or at the intersection of two lines as a position on a line. Semeia are alphabetic letters used in the mathematical context, but the deep fundamentals, the first mathematical structure that I know that is still now a mathematical structure, is the invention of the line with no thickness. That's why, for 1 century, my colleagues, the formalists, have been telling us that Euclid is the inventor of the axiomatic method, which is true, of course. In the Agora, they invented logic and reasoning, and Euclid is very rigorous. But it's for the other 50% what matters, which has been denied for 1 century, is the invention of the first fundamental mathematical structure, the line with no thickness, that I see in a sort of conceptual continuity with the previous inventions we made as human beings. But then, of course, there is the other part. As I said, these things cannot come without language. Only in language you can say, look, this line is not with no thickness, because indeed, when you draw it, it has a thickness. So language is necessary together with drawing to get the continuity of a line with no thickness. As I said before, I think the particular original invention with writing is the one of the alphabet. Those crazy guys, the tribe of Altam, as Clarissa discovered by her work, suddenly have been able to write a musical notation for the pitches of language, P, T, P, etc. And then, of course, there were the other forms, but the alphabet singles out by this particular abstract notation that is made of symbols with no meaning. You have to forget the meaning. The alpha apparently is the head of a bison, but folding on a side. If you remember this, you can't read anymore. You have to forget any meaning to put together and produce by phoneme a sound. You have to make the sound in the voice. By the way, that people have been reading loud till the 3rd century after Christ, apparently. And Sant'Ambrogio in Milan, who was the head of a group of priests who started reading in silence, was considered a sinner, and the Pope wanted to condemn him. as happens so often in the Catholic Church. Instead, he became a saint, but I mean, he was bordering line because he invented silent reading. Apparently, up to the 3rd century, the Roman and the Greek were always reading loud, and the fact of reading in silence, escaping to the control of the priest while reading, was considered, of course, something heterodox. That this role of writing acquired its own autonomy. I mean, there is this algebra of thought that Leibniz formalizes beautifully, together with many other things. Leibniz was exploring almost everything. So as a manipulation of meaningless signs, this is the strength, as I said, about the alphabet. Leibniz understands this can be really a technique for thought, the formalist, as reference to rules that allow to modify signs into signs with no reference to the meaning. This goes together with the importance of writing equations. Okay? Mathematics became, of course, the key tool for knowledge of nature with Leibniz and Newton. These are the laws of nature, when you can write them in equations. Indeed, the notion of law of nature stabilizes only after, with Newton's work, we can write them under the form of equations. But then, of course, in our boldness, we, the humans, we said, by this we can write everything, at least any dynamics. This is indeed what Lagrange and Laplace taught. You write equation of any mechanical process, they called it celestial mechanics, but they meant any reasonable physical process. You solve it, and you can predict the dynamics. Of course, I mean, this is a very bold enterprise, but these people made miracles with that. I mean, they really invented what became a fundamental tool for physics, differential equations. And Fourier and the others, all these people taught that any reasonable set of equations can be approximated in a linear fashion, so Fourier analysis. And again, this was fantastic mathematics, but they taught, now we can predict any dynamics. Why is this a big problem? Because Newton was aware that with these laws, one can derive from the sun and one planet the Keplerian movement and all Keplerian properties, which is the fantastic achievement of Newton. But if you have two planets, as the law of gravitation is universal, they interact, so they destabilize each other. How to treat this phenomenon? And Newton gave the only possible answer we have up to date to have the stability forever of the system of two planets and the sun. He said, God, time to time, goes back and puts the trajectories in their place. Why is the only possible answer? Because this problem of the three-body problem was proved to be not integrable and even not analytic. So you cannot provide a linear approximation to the equations, 9 equations on a plane of the three-body problem. This was a major result by Poincaré in 1892. So the writing of the equation is incomplete with respect to the world, in the sense, of course, that determination is correct, the system is perfectly determined, but because of non-analyticity, it's unpredictable, because that's the masterpiece that Poincaré did. He showed by purely mathematical methods, looking at equations, that they are not analytic, so there is no possible linear approximation to a solution. He gave geometric meaning to this, namely, he said, this means that there are bifurcations, that there are homoclinic trajectories, that is trajectory that are on a saddle, something like unstable and stable manifolds. He understands that in presence of these loci of instability, like a bifurcation, a minor fluctuation may give to very different trajectories. So he said, this is randomness. A minor fluctuation that I cannot measure below the best measurement may have a massive effect, observable measurable effect with time, because of the presence of this phenomena. Mathematical, purely mathematical phenomena. So he gave first geometric meaning to the absence of equation, of solution, and then a physical meaning to the absence of solution, say it is false. Even in presence of simply three interacting bodies, the nonlinear system, which is fully deterministic, is unpredictable, and we have randomness. So the completeness of the equation was shown to be false. Then comes Hilbert, completeness of the formal system. It's a kind of revision, but it's the same project with writing. I write the axiom, I can say everything about mathematical structures, you know. This was concerned any formal theory sufficiently expressive, in particular containing arithmetic. Of course, he knew of a Poincaré result, his major enemy, because they're very difficult philosophy of mathematics. So he says, any purely mathematical problem can be solved. Okay, I cannot predict physical systems when they are nonlinear and there are enough interactions, but I can decide any purely mathematical problem. So in a sense, he distilled the Laplace problem into a frame, which was also very interesting, by a very robust theory. Puff, Gödel theorem. No, this is false. As soon as a theory is expressive enough, I can produce effectively within the formal theory an undecidable assertion, in particular the coherence of arithmetic against an attempt of proving it by induction by Hilbert. The consistency of arithmetic is improvable. So the writing is always a matter of writing, logogrammatic and alphabetic writing for equations, alphabetic writing for the axioms in Hilbert's approach. Is incomplete with respect to what? In this case, with respect to the mathematical structure, what we inherit from the Euclidean line with no thickness, of course, enriched much more by the subsequent mathematics. It is a surprise for someone coming from those areas to go to biology and see that once again, they've been telling us that the DNA is complete. Exactly the same phrasing, even phrasing of the previous cases. You know, the first time, oh, fantastic, they invented partial differential equation. I understand they could have this bold idea that we can predict everything. Why not? I mean, that's reasonable. The second time with Hilbert is still very interesting because it's presented in a very robust way. Still, it is, let's be honest, a little less interesting. The axiomatic approach is important in mathematics, but it's not as important as the partial differential equations, The third time, my God, the same stuff, alphabetic writing, 4 letters. We can say everything about ontogenesis. The central dogma is exactly this. And it's a matter of writing. You see, François Jacob, a leading molecular biologist, 65. The surprise is that the specificity of genetics, it is written not by ideograms like in Chinese, but with an alphabet. We know on which side God is. I told this joke, but it's not a joke. I told it in China. We reached the compromise. You know, Chinese are very nationalist, so we decided that their DNA is written in ideograms. You know, otherwise, I couldn't get out easily from. So let's see what happens when we project this fantastic invention of ours, like the alphabet writing, into nature. Many give the responsibility of this to Schrödinger, and it is partly true, but he knew what he was doing. This is that beautiful little book, 1944, What is Life? It's divided in 2 parts. The second part is never quoted, and instead it's beautiful. Schrödinger is a major physicist and thinker. He's very happy of what is already happening in genetics. Molecular biology did not exist, but already chromosomes were isolated at the beginning of the 20th century by coloring that incredible, huge molecular structure in cells. And there was a remarkable work by 2 biologists, Badel and Tatum, who had been able, it was already done by others, but to not only observe changes in chromosomes. The DNA structure was not yet known, but the chromosomes were already studied, had been already studied for at least 40 years. They were able to see and even induce a change, a mutation, and then they observed that this was inducing a mutation, a change in a protein, in particular having enzymatic functions. So they said, 1 gene, 1 enzyme. Schrödinger begins his book by saying, this is not satisfactory. If you induce a difference and you see a difference, this doesn't give you the direct correlation. This is a differential analysis that requires a theory behind it in order to be a proposal for a causal correlation. So he said, the theory I propose in this first part, this is a coding, okay, code script, coded information. And he knows what he's doing. In calling the structure of the chromosome a code script, we mean that the all-penetrating mind, once conceived by Laplace, could tell from their structure how the egg would develop. Namely, once we have fully decoded the chromosome, we will be in the position of Laplace. Namely, we would be able to predict fully from this writing, from this coding, the coding. So it makes an assumption. Suppose that it is a code, but if I'm right, then once we will fully know the chemical structure of the DNA, the chromosomes, we will know perfectly well where ontogenesis will go. He knows what he's talking about. Then he has a second part, a very rich one about negentropy, reflecting how organization goes on. I've been working on that part, which has not been enough studied. The idea that this notion of coding is Laplacian, namely, once you have it, like the idea of Laplace, once you write equations, if they are correct, once you write equations, you can predict, is very clear also to Turing, the inventor of the logical computing machine in 1936. In 1950, he writes, in the discrete state machine, he doesn't call it Turing machine, but it's a Turing machine. In a discrete state machine, it's also possible to predict all future states. This is reminiscent of Laplace's view. The prediction follows. Again, both of them, they know what they are doing. If by coding we mean exactly the sense of Gödel and Turing, namely the bijective transfer of a same sort of structure into a linear annotation, then, of course, we have full predictability of the ongoing dynamics. That's the exact sense they ascribe to their work. They know what they are doing. But this has been passed over to a milieu where the lack of a previous history, ontogenesis, found a lack of theory. You see, in biology, there is a beautiful, fantastic, very rich theory. That's the theory of evolution. And you meet people really with depth and theoretical thinking. Unfortunately, we don't have a theory of organisms. So it has been replaced by this idea that there is a coding, a writing, there in DNA, which is complete, okay? Because, first of all proteins are coded there, and proteins make phenotype, the gene of. Let me quote some of the major theoreticians, because there are not many who theorize in molecular biology, because after the early 50s, genetics was transforming molecular biology, very different attitude. You see, the cell is a molecular process, a Cartesian mechanism, autonomous, exact, independent from external influences, oriented transmission of information, coding. I mean, Brillouin has been treating as an negentropy Shannon's coding for transmission of information. And this is a fundamental step. The early stereospecific molecular interaction explained the structure of the code, a Boolean algebra, like in a computer. So the idea that macromolecular stereospecific interaction means physiochemical exact interaction, the key lock paradigm. So the information is elaborated and transmitted by the fact that macromolecular interactions are exact like that and go on in cascades. Genes define completely the three-dimensional folding of proteins. The epigenetic environment only excludes other possible foldings. Evolution originates in noise imperfection. The concept of program gives now a legal status to teleonomy. But this is taken up as such also by a relatively recent paper by Minor Smith, who is another guy who sees evolution only in the changes of DNA. There, Minor Smith analyzes both the use of Kolmogorov-Turing notion of elaboration information and Shannon-Brillouin notion of information, and he finds them perfectly adequate to the biological treatment, falling exactly in these lines. So, which are the consequences of this transfer of the notion of information programming coding in biology? It started, as I said, one gene, one enzyme hypothesis, and Schrödinger is not happy with that, as I told you. He tries to propose a positive proposal. You know, this is known in physics. Galileo, when he observes the differences in friction, he makes a difference in the in the plane, inclined plane, and then he observes that friction induces differences he invents the principle of inertia. He understands that in order to have the positive correlation, he has to propose a general theoretical principle. He cannot rely on a difference giving a difference. The general law will allow him inertia, which doesn't exist. The inertial movement doesn't exist. You know, a point moving on a Euclidean straight line. But this limit movement at the horizon of all possible movements allow Galileo to understand all movements, because then he can analyze what affects, what modifies inertial movement, gravitation and friction. So that's the scientific attitude of which Schrödinger is conscious. Instead, there, the analysis continues in these terms. The central dogma is derived by the fact that changes induces changes and by the need of transmitting completely the information. And the exact stereospecific macromolecular transmission of information is the other component of this vision of the coding in DNA. And so the characteristic of coding which is taken on board without explicit discussion is the reversibility, at least the conceptual reversibility. Of course, you cannot physically go back from a phenotype to DNA, but conceptually, yes. Not only DNA determines the phenotype, but once you have the phenotype, you should be able every time, bijectively, to go back to the coding. And so the epigenetics has been excluded. First of all, those three facts are known to be wrong, all of them, and they've been guiding for 50 years, and still now, implicitly, many molecular biology rely at least on the central part of revised central dogma. Some say, oh, well, yes, it was a metaphor, you know, like the church after the French Revolution. Well, you know, yes, in the Bible, it's a metaphor, the reference to the sun that moves. But for centuries, they've been killing people on the grounds of the literal reference to what was written in the Bible. So for decades, they've been firing people, not hiring people. I know people who really have been excluded from the scientific community because they did not agree, okay? And now they say, well, no, it must be understood as a kind of a metaphor, same attitude. Now, saving the Bible is quite reasonable because, you know, the Bible is very important, so one has to save it. But saving the founding text of molecular biology, I really don't see the need. I mean, so even, I will insist very much about stereospecificity. The other severe fact, this has been excluding genetics. What is genetic? Well, you know, as I will insist, chromosomes and DNA are very important. My God, I mean, it's the physical-chemical trace of the entire history of evolution. We have it in every cell. It is a fundamental template that the cell uses to produce protein according to the context. So it's not a matter of excluding the relevance of DNA and chromosomes and all the mechanisms that molecular biology has been discovering there, which are fundamental. It's the theoretical frame that is totally wrong. In particular, this theoretical frame may exclude from quoting fundamental work in genetics. Waddington and McClintock have been working all their life, the first half of the 20th century, on chromosomes, because, as I said, they're very important. But they discovered the role of epigenetic phenomena, or regulation from the proteome, the membrane of genetic expression, from the context. They were excluded. I mean, Piatelli Palmarini, who is an Italian biologist, now in the States, who was a postdoc or a young researcher in the early 70s with Monod and Jacob, he wrote in a book and then told me also that they were forbidden to quote Waddington and McClintock and to visit them. Those guys already had the vision of the DNA inserted in the context. The other big point is that it was forbidden to think otherwise except for the exact coding going on by stereospecific cascade of molecules. And in chemiophysics, macromolecular interaction was already in the 50s were treated stochastically. You cannot see the interaction of two molecules unless you almost freeze them. And then, of course, they slow down, there are no more enthalpic oscillations. Then, roughly, the correspondence goes only by exact stereospecific interactions. But in normal temperatures, it was already viewed in a completely different way. Since '83, there were some pioneering work stressing the fact that macromolecular interactions are stochastic. They must be given in probabilities, and these probabilities depend on the context. This was denied. One of the persons who did that work is Jean-Jacques Opiec, a colleague of mine, totally excluded, and so on go, from the academic community, working in private sectors or with subordinated jobs because they taught something that now is acknowledged by a strong minority, not yet a majority, a strong minority, that gene expression and in general macromolecular interactions are stochastic. It's very canalized. It's not whatever, it's very canalized by the context. It's guided the stochasticity by the context. We know now that in any cell of your body, any gene is expressed. The point is the percentage, the probabilities, in very different probabilities according to the context, which guides gene expression. So it's the persisting myth, which is now active, is that any phenotype has an antecedent in the genotype. The genotype is a complete determination of the phenotype. One of the protagonists, a major molecular biologist, Walter Gilbert, in '92, says once they coded the DNA, he was working at that already, we will be able to transfer a CD-ROM and say, here is a human being, this is me. This is not kidding, because there's billions of dollars, okay, in the project. Selection targets only genetic information. Organisms are mere vehicles. They are avatars. And so we can find in the major journal the gene of marital fidelity, the gene of longevity, obesity. Of the first and the third one, I can tell you a lot, because I personally know a colleague who was very young at the time at Rockefeller Center, who worked at this, and who immediately told me, well, there may be some correspondence. Anyway, they sold that idea to a private factory, and they made a lot of money. And then more recently, she told me, that arnaque, I would say, this cheating has been sold to another industrial pharmacy. We now know that obesity has a genetic origin about 5%. The point is that 90% of the money has been going for decades to the search of those problems. Marital fidelity is real fun, because a colleague of mine made a close analysis of that paper. If you want, I can tell you. It's very interesting. I don't know much about longevity, though, but those two I can elaborate more. But a colleague of mine, Charles Lofray, who a former molecular biologist, made a collection. I think the particularly interesting is the gene of academic freedom. It may concern you. I trust he is right. Which is the myth there? The stability and organization of DNA and the subsequent molecular cascade completely determines the stability and organization of the cell and the organism by its complete informational content. This is false, because the very stability and organization of the cell and the organism causally contribute even to the stability and organization of the DNA and the subsequent molecular cascade. So the insight must be totally reversed without denying the incredible relevance of this structure, chemiophysical structure, the DNA. One has to see it as a constraint. I will try to hint this, constraining molecular activities in a cell, which actively uses DNA, starting with Brownian motion of molecules. Because, again, the incompleteness of those tools doesn't mean that they're useless. Equations in mathematical physics are the Rolls Royce of the work. I mean, the idea of completeness is wrong. But per se, and formal axiomatic theories are relevant in logic and mathematics. They are not as important. So this physiochemical trace of a history is really at the core of ontogenesis. And also evolution. What happened is that those guys who forced the wrong theory have been discovering fundamental mechanisms. I mean, the double helix, the structure of DNA is a remarkable insight, 1953. And also the work by Jacob, Monod, Changeux, Loff, discovering allostery and operon lactose. I mean, the experimental insight is quite remarkable. Operon lactose is a mechanism where a fragment of DNA, let's call it gene, controls the expression of another one. And it is correct, it's like that. The mistake was to take that as an absolute. That's the way how everything works. The control of DNA by DNA state is itself, like the operating system, which is written in 0 1s here, controls the programs. And indeed, Danchin, another colleague in Paris, has been looking very serious for decades for the operating system and the compilers in DNA, even as a paper on how unpredictability pops out by Gödel's theorem in the coding of DNA. I'm not kidding, I'm quoting this. So I'm in a paper and discussing what really means, something like that. So, but these fundamental discoveries have been embedded in this frame, whose consequence, major consequence, if I can summarize, are these two. First one, the purely fantastic derivation of an exact macromolecular correspondence, as I take again the quoting, the Cartesian mechanism, exact, independent for external influences, which are forces, in order to be transmitted, elaborated, the information, it forces it to go through exact macromolecular correspondence. External influences. Monod at certain point says that gene expression is independent of metabolism. That's incredible. You know, our ancestors 10,000 years ago knew that ants and bees modify gene expression by metabolism. Well, they didn't know the mechanism. Now we know the mechanism. But I mean, it is so evident that metabolism modifies gene expression. I mean, they denied it because metabolism doesn't contain information. It doesn't affect the coding. Like electricity here should not affect the coding, you know? And so the key locked paradigm, in particular concerning hormone receptors. An hormone receptor is a molecular structure where hormones affect the cell, modify the cell cycle, influence the cell cycle. The key lock paradigm is exact the idea that you can only have a key, exactly the one fitting in, that opens the lock, the cellular receptor. And the other one is a central dogma. These are consequences of this information coding theoretic frame for molecular biology that's been dominating for too long and still is very active. And so one can really understand what happened as a consequence of these two major theoretical principles that have been governing molecular biology for too long. How comes that we have been having so little attention to endocrine disruptors? And what are GMOs really? Now, the work I do is in collaboration with two biologists of cancer, Carlos Sones and Elena Soto at Tufts University, and from whom I learned everything on the matter. The situation with cancer is absolutely dramatic, you see, because with respect to all lethal disease, it remains stable in about 60 years. However, cancer medicine is very effective. The chances of being cured doubled in 60 years. So we have twice the chance to be cured because of external tools, essentially. Fantastic technology that allowed to discover cancer by a little camera that goes in your tissue, operations with laser, a remarkable clinical experience about chemotherapy. So they know how to mix them, how to act at the right moment on the grounds of clinical experience, fantastic interaction in the general networks of cancer medicine. I've seen the work of an histologist. He has images from all over the world to recognize a cancer. Well, by the way, I'm sorry to get into this because I know that all of us, directly or indirectly, are concerned with the issue. That's the dramatic situation where we are. Because I insist, incidence has been doubling in 60 years. And it is not a matter of aging because this contributes for at most 10%. It's a matter, in particular, of endocrine disruptors. This is the thesis of my colleague to which I totally adhere. the point is that most cancer concern activities where hormone system, which all over the body regulates cell reproduction, most of them deal with areas related to reproduction, which are in particular extremely sensitive to hormone control. So these are data concerning the increase for the time lapse. Thyroid cancer is the one that really marked a major change in our relation to this terrible disease. But besides cancer, there is another fact that also must be referred to endocrine disruptors, which I will explain what they are. Everybody has read, a couple of years ago, it was on all newspapers, I bet here too, that in 60 years, the spermatozoa density in Western men has been halved. I mean, that's gone to the newspapers, and there was very little reaction. This is effect of evolutionary relevance. If we were a wild species, we would be over, okay? But you know, we take care so well of children that by all means, even if we have only one or two, we take them to the age of reproduction, then we only care of the grandchildren. But by all means, we take them to that age, and there is an increasing number of artificial insemination. By these tools, we keep surviving. But this 50% is decreasing. Is there a threshold? We don't know, of course, but there may be a critical threshold. I don't know, 37%? Below that, there is no more fecundation? I have no idea. But that's the situation. There has been a very strong statement by the American Endocrine Society signed by 100 biologists, where they ascribe also this phenomenon to a cocktail, a finite combination of what? Of the endocrine, of the artificial molecules. Because you see, in the 20th century, we have been producing 82,000 artificial molecules and been placing them in the ecosystem. 82,000 of molecules that did not exist before. Most of them are small molecules. And which was the reaction of the most pertinent academic community, molecular biology? You know, they are not stereospecific. They are very different. They will not interfere with cellular receptor. They are not keys affecting the log. This is in papers for decades, okay? Small doses. This is all false, because again, there are low chemical affinities that matters. There are no linear effects. In particular, for finite combination of those molecules, the effects are non-linear. So if you fix a threshold here, it may go like this. It may be dangerous for a lower level. There are varying association constants, namely, according to the context, the association constant may change. Because as I said before, macromolecular interaction, in particular, the interaction of an hormone with the cell receptor is stochastic. It must be given in probabilities. It may change according to the context. There are low affinities, so the bisphenol A, I don't know if I will talk of it, the bisphenol A, whose carcinogenic effect was discovered by Salt and Sonneshan with students there in 91. Bisphenol A, it was known that it could give endocrine problems, but they discovered it's really carcinogen. A carcinogen. Bisphenol A at the time was produced by 2 million tons per year. It was present in all plastics for food, all of them. When Carlos and Anna started this fight, you can't imagine the way they were aggressive. Because, you know, when something is produced by 2 million tons and you say it's carcinogen, you make a few enemies. And these are ready to pay any kind of research discouraging this. So they received the observation, oh, you know, it is natural. Look at the yeast. It produces naturally. Then some other colleagues fortunately discovered that it was produced by the plastic containers where there were cultivations of yeast. Because of their commitment and of many others, that's been gradually forbidden. I met them 10 years ago, because they had an audition at the French and the European Parliament after an audition at the American Parliament that started 5 years earlier than in Europe, forbidding bisphenol A. That's the frame. I mean, they didn't only have industrial enemies, but they had the theory that said, don't worry, bisphenol A is not like estradiol, the hormone. It is somewhat different. It's not stereospecific. It will not act like a key. It acts on low probabilities. I don't know, the effect of estradiol maybe is 90% the time it bumps on the cell receptor. Maybe estradiol is 15, 20, but with time, it gives cancer. So this paradigm that is been governing too long, and still now, it is in the majority of the molecular biology community, it is in all newspapers, it is in the teaching in high school. All books of high school have this kind of image of biology, exactly that. I mean, I've been taking it from a high school book. I bet you had a similar experience. DNA regulating, guiding ontogenesis is something we have to get out. And there is the other problem, is the GMOs. The GMOs are the direct children of the central dogma. It's the myth that you act on DNA and you will guide the organism in the ecosystem. Completely, perfectly well. You know, I've been working with Marcello Buiatti, who's a genetician of plants in Italy, and he told me, we have been doing GMOs for 40 years in laboratories, but, you know, it was experimental work, and most of the time it doesn't work. Only 6 of them have some time of life in nature. They've all been commercialized. There are only 6 GMOs in commerce. Again, with the idea that you can guide exactly the organism, in particular their main feature is to resist to pesticides. There are many discussions about the side effects and so on. I learned from Marcello that the main ones concern the microbial flora and fauna, which is not enough discussed apparently, even though genetician of plants opposed to these follies know this since long. Namely, what happens is that the microbes and fungi on the roots of the plants that are an essential component of the humus and of the dialogue between plants are heavily affected by the pesticides that penetrate or by the radically different genetic structure of GMOs. Here you have some reference to cancer research. I'm finishing now a paper where I present some sort of mathematician's critique of this story. Now let's go briefly to a positive vision of knowledge beyond this myth of completeness of coding. So let's start with mathematics. First fundamental distinction. You know, all the AI stuff, excellent work. It's very useful to have a machine that makes a difference between a chair and a human. It's great, and it's very hard because, you know, it's a very machine to make it's fundamental. Always static images, of course. Well, we, the animals, we see only movement, but that's another issue. I mean, you have machines doing that stuff. It's great. But this is bringing a major confusion. They claim that intelligence is elaboration of information. No. Intelligence is production of sense, like those humans I said before that suddenly started making sense of the little lights in the sky by saying, look, this is a lion, this is a bison. And they made sense of it. That's production of sense. That's intelligence, which is very different. A minor component of it is the elaboration of information. The examples I gave were inventing the notion of border is a gesture of intelligence, which is not elaboration of information. There is no input there. There is an active way of singling out an image, of qualifying reality in a very abstract way. As I said before, this gestalt at the foundation of mathematics, the line of no thickness, the contour, symmetries. I mean, all the axioms of Euclid maximize symmetries. They really provide by diagrams this organization organization by figures of the plane. It is done both for practical purposes, but it is a praxis, I agree, it's also a practice when it is done as a dialogue with the gods. It's this double role of Greek geometry, which is an ontology and a practical issue, anyway, conceptual practice, that gave it strength. All the proofs, all the proofs are given by rotations and translation with no numbers, as Roy remembered before. There are just one, I think, or two theorems about numbers, like the prime number theorem. And a line for Euclid is not made out of points. It's a gesture. The axioms say produce, trace. It's a continuous gesture in a phenomenal continuum of movement. I think we have to understand this construction of knowledge we practice in the works of Husserl, quite beautiful in The Origin of Geometry. Geometry is embedded in our space of humanity, beginning with the human activity. And of course, the problem of continuity is a major one. As Hermann Weyl says, the conceptual world of mathematics so foreign to the intuitive continuum presents to us the demand of coincidence between the two must be dismissed as absurd. Nonetheless, we do provide tools for continua. Cantor's approach is fantastic, probably the most robust one we have so far, but there are other ways. There are non-standard continua, the topos theoretic continua. And on the lines of what Roy said before, Hermann Weyl observes, by pointing toward the essential historical nature of that life of mind, of which my own existence is an integral but not autonomous part, it is necessity and contingency, bondage and freedom, and it cannot be expected that the symbolic construction of the world in some final form can never be detached from it. But symbolic construction, as the meaning that I gave here, those human practices of singularizing invariance, since the early drawing of lines between stars or the drawing in Lescaut and Altamira caves. I should say perhaps a few things about biology also, which is an historical science. The real challenge of biology is that it is a science of nature, no doubt. There are observations and experiments that makes it a science of nature. However, it is an historical science. So everything in biology can only be understood in view of evolution. And the challenge is that the object of biology, phenotypes and organisms, are historical, specific, while the trajectories are possible ones. The other challenge is to question, can we give a priori the space of possible trajectory? The point is that we have to decide which are the observables, and Darwin opened the way. Darwin observed phenotypes and organisms. It is the theory which decides what can be observed. Darwin has two principles in his analysis of the trajectory, phylogenetic trajectories of organisms and species. People very often mention only the second, but the first one, descent with modification, spans 3 chapters out of the first 6. And is also as revolutionary as the second principle, selection, because Buffon and Lamarck, to whom Darwin refers in a very positive way, they were evolutionists. Buffon and Lamarck thought that the ecosystem was inducing changes, while Darwin insists that any reproduction yields a change, a modification. Maybe a small one, but any reproduction gives a modification. There is variability that is implicit to life. Any cellular reproduction, if a cell reproduces, the proteome doesn't split exactly. Many molecules are present in one molecular type. There are only 100 molecules. Then at the splitting, 53 go on one side, 47 in the other. The same with DNA. That's the least level of variability that is present in life. Every reproduction, there is a change. Then selection. That's the perspective. The first principle of Darwin, I insist, is the core of his approach. Darwin insists very much on this. He even says the breeders, his reference for inventing selection were the breeders, even if when they like a species or a variety of an animal, they cannot stabilize it. He says there is no case where reproduction doesn't yield some sort of change. So the breeders have difficulties if they have a cow, which is fantastic for the amount of milk it produces. At reproduction, it may give a different cows. And he says there is no way to stop change. And that's the first principle of evolution. In a sense, it's the exact opposite of what was happening at the same time in physics, where Hamilton, by conservation principles of energy and momentum, invented the variational method. So it's the moment where physics is understood in terms of conservation principle. Inertia was the invention of Galileo, the real invention of modern physics. But by the appreciation of conservation of energy, in the 19th century, we could do this incredible miracle, Hamilton, the Hamiltonian, from the Hamiltonian you can derive Newton equations, from Newton equation you derive Kepler orbits, and also from the Hamiltonian, later on, it will be possible to derive Schrödinger equation, this great unity of conservation principle. The first principle of Darwin is a principle of non-conservation of phenotype. Phenotype is not conserved. The point is that since the phenotypes are our observables, what changes is the phase space, the space of possibilities. Physical theories have different phase spaces. Each theory, according to the scale, quantum physics, relativity, of hydrodynamics or chemistry, have different phase spaces. But once the theory is set, the phase space is stabilized. This is what changes instead in biology, and it is the real mathematical change. There is not such an invariance as it is proper to conservation principles in physics, which of course are underlying. They must be respected, but organisms don't care to conserve energy. They use it as much as they can. They canalize it and use it. Very shortly, at the challenges that I'm working with my colleagues for a theory of organisms, which is a component of a theory of evolution, okay, is that one has to understand how the future depends on past and rare events. Namely, rare events are crucial. Any phylogenetic trajectory is given, punctuated by rare events. The awful monster, which gives speciation, is very rare. And it is very rare that awful monster finds an environment where a new species, a variant, originates. And the other point is that emergence is not necessary. In physics, a hurricane, a snowflake emerge, and they are necessary in the sense that for certain values of parameter, you surely have a hurricane, you surely have a snowflake, you don't know the details, you cannot predict because it's nonlinear. Most phenotypes in biology are not necessary. There are plenty of fishes of deep sea, and this guy, as a kind of, lure to fish other fishes, was not necessary. The point is that the work is to understand differently randomness, because randomness affects the very phase space, and predictability is the very phase space. And it's not noise. That's the other incredible deformation. The wording is not meaningless. It's meaningful. Calling, as Monod does, and the others of new synthesis, randomness, noise, it means that you're referring to noise, what is at the core of evolution, variability, diversity, and adaptivity. Indeed, I think that calling noise diversity is more politics than science. Can we optimize adaptivity? That's very hard as well. Because, 99% of species that were born on Earth are extinct. It's not fantastic as success. Indeed, the only successful ones are the bacteria. You know that still now the bacteria form 50% of the biomass, not the number, the biomass, 50%. If you dig 2,000 meters below 8,000 meters of sea for searching oil, you find bacteria still living there. Perhaps they're also very happy, I don't know, but I mean, they still dominate evolution. They are the only successful one, honestly. So it's not. Well, don't go any more in details. I think I should stop here. That's just a frame we have to invent. We are working at moving from that kind of picture that's been dominating for too long to another more complex story of interactions that may allow to understand, in particular, the major role of DNA. And here are some references.
which is not a coding.